that says everything's relative. And they love to apply that quote to things that aren't physics. People love to apply it to their lives to say, well, my life's difficult. Oh, everything's relative. Sure, compared to some of the other stuff you have experienced. Really, those quotes don't belong there. Applying physics quotes to things that aren't physics is, in my view, blasphemy. But, you know, that might be a little extreme. So when we talk about something being relative and what a frame of reference is, we've got to consider only the physics concepts, because only then does it actually make sense and not become a subjective argument. So a frame of reference is a stationary point, and I'm going to put big quotes around stationary, point from which motion can be measured. Motion can be measured. So when we talk about your frame of reference, the frame of reference that you exist in, you can consider to always have zero velocity, always to have no motion. So my frame of reference up here, as I was walking back and forth, I would consider to have zero velocity. And rather than me be moving compared to you, you were all moving back and forth, left and right, at approximate speed of 1 to 2 meters per second, a total of 5 to 6 meters, compared to my frame of reference. So your frame of reference is always considered stationary. All right. It is not actually velocity that we can experience and we can feel, but it is only acceleration that we can actually understand happens. If we understood velocity to be acting on us, if we could feel velocity, we would be able to feel ourselves whipping around on Earth. We would be able to feel ourselves cruising through the solar system. But we can't feel that. Because we can't feel that, we know we can't feel velocity, and therefore we only feel accelerations. So a frame of reference can only, and I'm going to put feel because that's what we as people experience, accelerations. We know this to be true because if we consider riding on an airplane, it's a nice, easy ride. When do you notice that you're really on an airplane? There are 3 times, really. Takeoff, landing, turbulence. Absolutely. Those are the only 3 times you really notice that you're actually on a plane. Otherwise, it feels exactly the same as standing on Earth. Now, maybe your ears have popped. Maybe you've got a little bit of panic. But in terms of how your body actually senses things, only during takeoff, landing, and turbulence do you actually feel something, because those are the only times you experience accelerations. Otherwise, you can look out that window, and it appears as though Earth is whipping underneath you and spinning just in a different manner. You don't observe that the plane is feeling thrown forward. Makes sense? Okay, it's a weird concept initially, but then once you consider that you've actually experienced it on a plane, maybe a train, at least in a car that's cruising, you can recognize that, yeah, that's something that I can make sense of. We can also use frames of references calculationally to understand what an observed velocity could be. So one of the ways you may have experienced frames of reference is, of course, in your car. So let's say, relative to the surface of Earth, your car is going forward at 80 miles an hour.
Sorry, could I have Abraham Bukhari to the office, please?
Will do.
Thank you.
See ya. So your car is going forward at 80 miles an hour. If you're going to drive past a tree, there's my tree. Relative to you, what does it appear that the tree's velocity is? 80 miles an hour? Negative 80. Why negative 80? Right. So if we are driving this car and relative to Earth, our velocity is 80 miles an hour, then relative to us, a tree that's on the surface of Earth would appear to be coming at us at negative 80 miles an hour. So whenever we're going to consider our frame of reference to be 0, that means that we can attribute our velocity to outside objects simply by subtracting that value from both objects. So velocity of one frame of reference can be transferred to other frames by subtracting the value from both. To other frames by subtracting the value from both. So in this example, we have the car, and it's at 80, and the tree, and it's at 0. We subtract 80 from both, and we find that the relative velocity from the car's frame of reference is 0, while the tree's is negative 80. So this would be from Earth's frame, and this would be from the car's frame. Okay, now to make it a little bit more interesting, you observe another car coming down the 2-lane road at you at 75 miles an hour. This one's a smart car. It's teeny. Okay, first of all, relative to Earth, what is the new car's velocity? Negative 75, because we drew it going the opposite direction. So I'm going to draw in negative 75 there. So car 2, negative 75. Therefore, what would be the observed velocity relative to your car, car 1, that you would observe car 2 to be coming at you with? Say how much? Negative 155. Because again, we can subtract our frame from the other frames in order to determine what the observed velocity must be. This is something that police cars have to be able to do when they're detecting your speed. If police cars don't account for their own velocity, then they attribute their velocity to you, and suddenly you're going way faster. So not only do the devices have to use Doppler effect, which we'll talk about later, but they then have to be tied into the vehicle's, the cop car's speedometer in order to account for the policeman's own velocity, which also means that it's easier for them to pick up velocities when they're not moving. Okay? Questions about these frames of reference questions? Yeah, Nate.
If we have questions like this for anything, will they have like directions to where you kind of like
What the relative frames of reference are? Yeah, absolutely. Yesterday we also discussed positive versus negative in terms of it being kind of arbitrary.
Excuse me, could I have Fred and Katie come in office, please?
Will do.
Thank you.
Are they going to take my whole class? So most times we will be considering Earth's frame of reference to be 0. Beyond that, though, how you decide to set up a problem like this, which way is positive, which way is negative, is arbitrary. So telling me that the velocity of the oncoming car is negative 155 tells me two things. One, you got the magnitude figured out. 2, by assessing it to be negative, while this one was positive, you're telling me it's in the opposite direction. Had I chosen this to be negative and this to be positive, how would my answers now change? Right, I just flip each one. So this would now be negative. I'd subtract negative 80, which would be adding. This would still be 0. And subtracting negative 80, subtracting negative 80. This would be positive. This would be positive. This would be positive. And suddenly I change the direction to having these both in the positive direction. In terms of me grading things, and in terms of, for those of you taking the AP test, in terms of an AP grader grading things, we have to be aware that there's possibly more than one right answer. Positive 155 and negative 155 are both equally correct because the individual doing the problem has set parameters of which direction is negative. In this case, this would be negative, and this would be positive. And we have to be aware of that potential difference in terms of just watching to make sure, well, what did the person doing the problem say is positive and what did they say is negative? Because, again, it's arbitrary and up to the person doing the problem. Did that answer your question? Okay, good. All right. Frames of reference. Questions on these? It's really a conceptual problem because the math is like second grade math, maybe. And this is actually something that Einstein used when he was developing his theory of special relativity, is trying to talk about frames of reference and how they apply to light. So while this is a concept that it seems like should be pretty simple, the ramifications of it can get a whole lot more complex as we're able to start looking at more extreme cases. All right. The next concept that we want to take a look at are motion diagrams. Actually, I'm just going to skip to the next page for that. Motion diagrams. You guys encountered 2 motion diagrams when you were taking the FCI. Possibly more than 2. These were the ones where they had things that looked like this, and a position, and an arrow, and they roughly appeared like that. That look kind of familiar? Hopefully I'm getting yeses from everyone. Okay, so a motion diagram is showing 2 things. 1, time. 2, the magnitude of a velocity or acceleration vector. Typically we go with velocity. So motion diagrams show time intervals and velocity magnitude. And this velocity, we could be talking about something else like acceleration, though that's much more rare. Okay? The purpose of a motion diagram is to get us to recognize that each of these dots represents an equal time interval. Maybe it's 1 second, maybe it's 2 seconds, maybe it's 3 seconds, it doesn't matter. They're all going to be at the same interval, and we can observe if we were to take snapshots of an event occurring and then overlay them on top of each other. This would be the kind of image that we start to get. So if I say roll a ball from here down to the end of the aisle here, and we were to take an overhead picture every second, and I rolled it at a constant velocity, you'd see the ball in this spot in one picture, and this spot in the next picture the next second, and this spot in the next picture the next second, and so on. And then just by overlaying them on top of each other, we get our motion diagram. We can determine if something is speeding up or slowing down in these by the distance between, wow, I think I'm drawing these incredibly constant. By the distance between points and the magnitude of the arrows that are representing velocity or in some cases acceleration. So in this case, if these again were to each be taken as a snapshot 1 second later, what would the object be doing? slowing down because we've got smaller distances, smaller displacements between equal amounts of time. Conversely, if I had a second object where I was drawing them a little bit more like this, what would you be able to tell me about the object? Speeding up. Why? Longer magnitude and bigger space between, bigger intervals. Yeah. So if these are the same time interval and it's traveled more distance in this time interval than in this time interval, then it must be speeding up. Again, easy concept, but if it's the first, or rather the second time you've seen it, it might not be necessarily intuitive. So let's go ahead and take a look back at that FCI, and let's talk about those couple problems that we actually ran into on that.